Today's focus will be talking about matter. Matter is made of particles that have a definite mass and volume. Okay, so it has to have both mass and volume in order for it to be considered matter. What is mass? Mass is a measure of how much stuff an object has. So if I say it has 40 grams and then this other one has 80 grams, the one with more mass has basically more stuff. Volume is a measurement of how much space an object occupies. So how much of a space it takes up. Okay, so it's matter has to have both stuff and that stuff has to take up space. So what is an example of matter? Basically anything that you can tangibly see or touch or feel is going to be this matter. Okay, so what is matter? We've got gas. Okay, we've got the gas that we breathe, we've got gas we put in our cars, we've got water, we have books, we have, let's say, tables, we have animals. These all have some sort of matter because they take up space and they have some sort of stuff involved in it. Okay, what is not matter? Well, you've got magnetism, electricity, light, sound. These are all different examples of things that do not have mass nor take up space. So how do we measure matter? So there are different ways, depending on what we're trying to measure, that we measure it. Okay, and what we use in science are these SI units. It's an international system of units known as the metric system. So we use the metric system. Always in science, what we want to do is we want to use the same measuring units. And the reason why is so I can compare my results in the US to those results in England without having to do any side of conversions. It's just a straight on, everybody understands the language that we speak, and that is the metric system. There are certain base units that you will absolutely have to have memorized. And my guess is most of you guys already know these units. The first one is to measure length. We measure in science class them in meters. It is abbreviated as a lowercase m. Okay, so the basic unit, if we're ever trying to measure something with length, is going to be in meters. If we were measuring some sort of volume of matter, okay, the volume unit will be in liters, and that is a capital L. Okay, so the base unit for volume is liters. And then the base unit, if we were measuring mass, which is once again how much stuff it has, will be in grams, and it is abbreviated by a lowercase g. Okay, so we have length is in meters, volume is in liters, and mass is in grams. Now that's all fine and dandy to know those base units, but the thing is that what's amazing about the metric system is it's based off of tens, okay? So all you have to do is either add a prefix to make your number, your base unit bigger or smaller, okay? And these are the ones that you're going to have memorized. You have deca, you have hecto, you have kilo, okay? So a deca means that you have 10 of your base units for every one of your deca unit, okay? So let's say my unit, and it should be DA. Okay, so let's say my base unit is liters. So what it's saying is that we have 10 of my base units, so 10 liters is equal to 1 decaliter. We have hecto. Hecto, there's 100 of your base units for every one of your prefix unit. So what that means is I've got 100 grams for every one hectogram. Sorry, hectogram. That looks awful. Let's try that again. Hg. Then we have kilo. Kilo, there are 1,000 of your base units for every one of your prefixed unit. So we're saying there are 1,000 meters to equal 1 kilometer. And this comes into play, you want to use these prefixes because it comes into play when you're talking about really, really big numbers or really, really small numbers to be able to put them into better understandable units. So it's easier for me to visualize, let's say 7 kilometers, right, as a distance as opposed to 7,000 meters. Okay, if I had to run 7 kilometers, I can kind of visualize how that is compared to 7,000 meters, a little bit easier. And that's because this is 7 versus 7,000. Our brains can wrap around the 7 a lot easier than that 7,000. Okay, now you go down to the deci. The deci means that what you're going to have is you're going to have, the deci are for smaller units. So for this one, you'd have 1 of your base unit for every 10 of your deci units. So let's say we're talking about mass. So mass would be used in grams. So we're saying 1 gram equals 10 decigrams. Centi would be 1 to 100. So 1 meter equals 100 centimeters. And then milli is, let's say 1 milliliter, or sorry, 1 liter equals 1,000 milliliters. Let's try to do some conversions, and I'm just going to introduce you to this topic, and we'll be dealing with it a lot more in further topics. But if there are 1,000 grams for every 1 kilogram, calculate the number of grams in 35 kilograms. So what we're going to do is we're going to start how you start these conversions, and this is called dimensional analysis. How you start it is you always start with the number that I'm giving you, not a conversion. This guy right here, for every, if you ever see a for every, those are going to be your conversions, okay? So what you do is you always start with the unit, the number I give you, which is 35 kilograms. And what I'm asking you to do is go to grams, okay? I'm asking you to convert this into grams. So what we're going to do is we need to set up a proportion, okay? And this is going to be new, so just pay attention of how I do it. And once again, we will be emphasizing this in further videos. So right now it's just kind of seeing it overall. So what you want to do is you're going to set up this like T conversion chart. And whatever unit you have up here has to go down here, okay? And the reason why is because those units, if they're on top of each other, they will cancel. So let's say I had X times Y, okay, as far as units, divided by X. What happens is that my X's would cancel. That's going to be the exact same philosophy here. So if I have kilograms up on the top left, kilograms automatically has to go on the bottom right immediately, okay? And whatever unit you're trying to go to will go on top. Now I know a direct conversion between kilograms and grams, so I can go to grams right away. And now all you need to do is put in your numbers. So it's 1,000 grams for every 1 kilogram. So you put in the numbers that are associated with that unit, okay? And so now if I look at my units, my kilograms is on top and then it's on bottom, so it cancels, and I am left with grams. So what this ends up to be is 35,000 grams. All right, let's try the next one. Okay, for if there are 100 centimeters for every 1 meter. So that automatically means that those are conversions. So I'm going to use it in this T part later on. Okay, calculate the number of meters. So I'm finding meters in 245 centimeters. So I'm going to start with 245 centimeters. Okay, going to set up my T chart. Where does centimeters then have to go on my second part of this? Centimeters has to go on the bottom so that the units of centimeters can cancel, okay? And now I know a conversion between centimeters and meters, so I'm going to put that up here, my meters up here. The only reason why I can put up meters up here is because I know that conversion. So now what I'm going to do is I'm going to look at these numbers that go with these units on the conversion. So I'm going to put 1 with meters, and I'm going to put 100 with the centimeters. Now I'm going to multiply it out and divide. So what that does is you multiply, so 245 times 1, and then divide it by 100. So you get 2.45 meters. How did my units cancel? You look at centimeters. Centimeters has canceled. Meters does not cancel because there's nothing to cancel with. So that's what I'm left with is meters. So my final answer is 2.45 meters. All right, and then the last thing that we're going to talk about is the law of conservation of mass or matter. What this law states is that matter or mass, so stuff, can be only rearranged but neither created nor destroyed. Okay, so basically what that ends up to be is that even if it changes its appearance or it combines with new things or whatever, matter, the amount of matter you start with has to be the exact same amount of matter you end with. Okay, so however much you start with, you have to end with the exact same amount. Okay, so what we're going to try to do is apply these with something we call particle pictures. I'm going to want you to draw a particle as a circle, not a dot, but a circle. Now you can color that circle in to represent a different particle. You could also do a square, but really what I really want you to focus on are circles. And if you need to do different particles, then just color that circle in or put an X through a circle or something to try to make it represent a different particle. Okay, so the first one is I need to draw before and after of particle pictures that illustrate the law of conservation of matter and mass. So knowing the law of conservation of matter and mass states that matter in the beginning has to be the matter in the end, which if I then fill in with my layman's definition of mass, the amount of stuff I start with is the amount of stuff I have to end with, okay, which means the amount of particles I have to start with is the amount of particles I end with. I need to represent that. So you literally need to count your particles in the beginning, picture, and count your particles in the end, and they have to be the same. So the first thing I'm going to talk about is melting of ice. Ice and melting goes from a solid to a liquid. So what I'm going to try to do is draw a solid, and I'm sure you guys are very familiar with how people draw solids a lot. They draw them together, right? So how you're going to draw this solid is you're going to draw circles. So I'm going to have, I always like to do typically like 9 particles. So I draw those 9 particles, and that is a solid. How do I know it's a solid? Well, it's maintaining the shape, and it's not taking the, meaning it's not taking the shape of the container, and it maintains its volume. Now this represents the solid part. Now I need to translate it to going to a liquid. So the laws of conservation of matter and mass states that the amount of stuff needs to stay the same, but it can look a little bit different. So how will I represent a liquid? Well, liquid, you just draw a squiggle line. Okay, and then you draw your 9 little particles. So that's 6, 7, 8, 9. Liquids are more random, and so that's why I draw it like that. Okay, so notice my amount of stuff stayed the same, but it does look a little bit different. All right, now I'm going to draw a chemical reaction. Okay, so the first thing I'm going to do is, you guys don't even know really what, it's just something, let's say we're just combining things. So what I'm going to do is I'm going to draw a substance. This would represent a solid to me if I were looking at it. And then I'm going to draw some gas. Notice that it's floating in the container and stuff like that. So that's my before. So now I'm going to undergo a chemical reaction. So what does that mean if the law of conservation of mass or matter needs to say? So I need to show something changes, but I also need to make sure that my amount of particles are the same. So I started with 9 orange yellow particles. So I'm going to end with 9 orange yellow particles. 2, 3, 4, 5, 6, 7, 8, 9. And then I need 3 purple particles. 1, 2, that's a really bad one. 2, 3. So notice that it does change what it appears like, but if I counted the individual particles, they would be the same. Therefore, the law of conservation of mass or matter was maintained. All right, hopefully you understand that matter has to have both volume and mass mass is how much stuff you have. Volume is how much space it takes up. We measure matter through the SI units, or the metric system. Grams measures mass, liters measures volume, and meters measures distance. If you want to change or make those smaller or larger numbers, how we tend to do that is we add prefixes to it. So you've got the deca, the hecto, the kilo, and things like that. You add that, okay? Through conversions, you can then figure out what are the equivalent values. So if I have 100 centimeters, how many kilometers is that? And you can do conversions through that. And then the final thing is the law of conservation of mass states that the amount of stuff you start with, the amount of particles, has to be the same in the beginning as in the end. Have a great one.